The train problems first, and then the Atwood machine problems. It says there are 15 toy rail cars, all at the same mass of 0.2 kilograms and very little friction between their wheels and the track, all connected in a row on a level track system. The phrase "very little friction" allows you to say no friction. You just assume it's zero. So negligible, very little, that's code for zero. So in case you thought you had to deal with friction, you don't. What is the tension in the coupling attached to the last car? What is the tension in the coupling attached to the seventh car? Saying attached to the seventh car is a little bit ambiguous. Do they mean the coupling between the seventh and sixth car, or the coupling between the seventh and eighth car? I'm going to do seventh and eighth, but you'll realize that when you're done, the process would be the same for the sixth and seventh. So I hope that all of you realize you do not have to deal with 15 cars. That once we realize there's no friction, level ground, and everything's being treated the same, I could find out the acceleration to all of the cars by just looking at a single force acting on one box. That is 15 cars of 0.2 kilograms each, for a total of 3 kilograms for the train. If I treat it in this manner, that means that the net force equals ma, or 3 newtons equals 3 times a. So a equals 1 meter per second squared for the whole train. Good so far? All right. So that means every single car experiences an acceleration of 1 meter per second squared. So I'm going to separate the cars into 14 cars and 1 car. So the 14 cars are 2.8 kilograms, and this wee little car is 0.2 kilograms. Whether I talk about the 14 cars or the 1 car by itself, they all have the same acceleration. So the 1 car by itself is accelerating at 1 meter per second squared. It's experiencing a tension force to the side. So net force equals ma for that car. That means tension equals 0.2 times 1, or 0.2 newtons. Any questions about that? All right, good. So the tension between the 7th and 8th car, or the tension between the 6th and 7th car, procedure would be the same. I can break this up however I like. I don't have to break it up into individual 15 cars. I could break it up into 7 cars and 8 cars. The tension in the coupling doesn't know that there are individual cars behind it. It just knows that there's a mass of cars that needs to be accelerated. So in this one, I'm going to treat it like 2 cars. One that is 7 cars times 0.2, or 1.4 kilograms, and 8 cars times 0.2, or 1.6 kilograms. That means there is a single tension that acts on those 8 cars combined. That net force has to equal ma, so T has to equal 1.6 times 1, or 1.6 newtons. That's it. Now, if you interpret it as being the tension between the 6th and 7th car, you would just change that up and move it to be 9 and 6 as opposed to 7 and 8. All right. All right. That's good. So go on to number 4. I don't know about senior night tonight. I think it's probably going to be indoors. But maybe there'll be a break in the clouds right around 5 o'clock. Get 3 hours of nice sunshine. But I don't think so. Number 4. 2 boxes are on the floor, mass M1 and M2. There is negligible friction between the boxes and the floor. You are to push the 2 boxes across the floor with an applied force F. Find an expression for the normal force between the boxes in terms of M1, M2, and F, and any fundamental constants that you need. This is an ambiguous question. We don't know which side of the boxes we're pushing on. That's intentional. But I think that when we're done, we'll probably be able to interpret our response enough to address either side. So I'm going to set the problem up like this: M1, M2, and my applied force is here. Any question about that? So I'm going to start by assuming that there's negligible friction. The system is going to accelerate because I have an unbalanced force acting on the system. And at this point, I could, from the very beginning, just say that net force equals M1 plus M2A and find the acceleration this way. There's no reason not to treat it like one box. So F equals M1 plus M2A. We've talked about this enough where we should be able to cut to this without doing it the long way. However, because I need to find the normal force anyways, I'm going to go ahead and do it the long way. There's no friction, so I'm going to ignore the up and down forces and only worry about the sideways forces. And box 1 is experiencing a sideways force of F and another sideways force in the opposite direction of N. That good? That means box M2 is experiencing a Newton's third law pair force that is also N. And that is all of the forces acting on our individual objects in the system. Now, over here, net force equals M2A. So normal equals M2A. I haven't said this, but I'm making this direction positive. And this side, net force equals M1A. So force minus normal equals M1A. Clearly, if I add these two things together, when I add them together, I get this. Everybody see that all right? So I don't think I need to add them together since I already have it up there, but it's good to know that everything works out. If I want to get an expression for the normal force, then I need to eliminate A between these two. I think the easiest way to do that is to solve for A here and substitute it here, since this is the simplest form. So I'll notice that from here, A equals my applied force divided by the sum of the masses. And when I plug it in over there, I will get normal force equals M2 over M1 plus M2 times F. Huh? I didn't. I plugged the acceleration here. Is that okay? Now, you should consider the fact that the force could have been over here. And you should work out what that would do to your answer. It doesn't make much of a change. And I would encourage you to verify that if you do that, you get this. You should try it. The answers aren't the same when you push on either side, and we've already seen that in a couple of the examples we've done. You should verify that this is true. This also tells you that if you want the force to be smaller between the boxes, put the smaller box at the end. That's what this tells you. I'm expecting you to be able to make that interpretation. You know, the order matters. What order would reduce the force between the objects? At this point, I've tried to put that in front of you as many times as possible. You really should be looking for it. And looking for that is a question I'm going to ask on your test. Any follow-up for this one? All right. So this is now in the Atwood machine question. It says, consider question 3. Is there anything you could do to them? Why would I do it that way? I think I was supposed to say consider question 1. It doesn't make any sense for me to ask consider question 3. So if I'm doing this one because you're wondering why did I say question 3, I'm with you on that one. Probably what was happening is that when I put the labels in for Train and Atwood, it renumbered them, and I'd already written the problems out. So I am happy to explain it either way, but I think I was supposed to reference number 1 there. Would you still like me to reference number 1 and do it? Yeah. Okay. What I'm going to show you guys is a problem that has been on many multiple choice tests, including, if I recall correctly, some semester exams. I don't know if this problem is still out there. It is intentionally deceiving. So I hate it when I see this problem on a test, but I figured we might as well discuss it because if it shows up, I'd like you guys to be, prepared for it. Man. Homecoming came here and all of you got some crap. Glad that we are all coming to school to share it. Of course, I get mad when everybody stays at home. But boy, all the snot and coughing. I'm going to be wearing a mask forever because you germ bags. Yeah, that. Knock it off. Hold it in. You're not. Nobody should. Keep your little phlegm inside. Well, actually, the way I look at it is, and I'll hit the pause here. Here we go. In this problem, there's a couple things here that are deceitful. This problem isn't deceitful in that I know from the work that we've done so far, if I make it frictionless, you guys should be able to work out an expression for the acceleration of the system. We've talked about this kind of question already. However, a couple years ago, they had a problem that was similar. What they did instead was they put a situation that had I think a 10 kilogram block up here. And they had a situation with a 5 kilogram block here. Then they had a situation that was similar. But instead of having a 5 kilogram block, they left the 10 kilogram block on the table, just like it was. Oh, not like that. but they just said that they pulled down with 50 newtons of force. And they asked to compare these two things. A shrewd student would look at these and say, well, this is a 50 Newton weight because it's 5 kilograms. And they would assess that the system would behave the same way, that these two systems would have the same acceleration. And that's wrong. And that's supposed to be what the Atwood machine is about, identifying this as two different situations. And for those of you who don't know why these are two different situations, or for those of you who are confused as to why I'm bringing it up, that's what you've missed in the small talk that I've tried to say between the problems that you didn't write down. Which of these two systems has more inertia? The one on the right or the one on the left? If you don't know which direction to point, you're going to be the ones that I'm going to be able to easily fool on your test. But on one side, 15 kilograms of mass has to be accelerated. And on the other side, only 10 kilograms of mass has to be accelerated. Me, an external force pulling down on the string, my mass isn't accelerating. I'm just applying a force to a system in which 10 kilograms has to accelerate over here. But on this side, all 15 kilograms has to accelerate. The unbalanced force in both of these is 50 newtons. But the right side will have a net force equal to 10A and a 50 Newton force that is accelerating that mass. This will have an acceleration of 5 meters per second squared. This side, when you are done with your Atwood machine work and you've done all the forces and eliminated the tension and found the acceleration, you'll get 50 newtons equals 10 plus 5 times A, and your acceleration will be 50 over 15, or 3.3 meters per second squared. On this side, the tension in the string is 50 newtons. On this side, the tension in the string is less. It has to be less than 50 newtons because I'm hanging a 50 Newton weight, and the only way it accelerates downwards is if there's less than 50 newtons of tension in the string. But you understand, in multiple choice, when you have a minute and a half to answer each question, and I present these to you, I bet those 4 choices are all going to seem plausible. You guys understand? I'm putting this in front of you because that's what the intent of question 2 is really about. To try and make you take a good hard look at what are the extremes here. Now, I'm bringing this in front of you because this question's been on exams and it keeps showing up. The numbers might be different, but I think you understand the intent of what this question is supposed to exploit. They'll put numbers on it intentionally to be deceitful. They might go as far as to not even put that this is 5 kilograms, that this is a 50 Newton mass. You can see why that's deceptive. So don't be easily deceived by that. Be paying attention, be looking for that. Now, if we just consider just a standard modified Atwood, where I'm supposed to compare and contrast as requested in the problem. So let me set it up real quick. There, so something like that. There are extremes, but if you've worked this problem out, at this point you know that the acceleration is going to be equal to m2g over m1 plus m2. So if I need to, I can show you where that comes from, but I don't know that I need to. So we're good with that? All right, what I haven't done is I haven't worked out what the tension would be, and it's not hard to work out the tension here. We know that M1 accelerates at A, and it's only experiencing a tension to the right. So if I combine these two, I can figure out what the tension is. You may not recognize this, but this is a form of weighted average. You've learned weighted averages in some of your classes, but that's what this is. It's a form of weighted average. And this would be the tension in the string. Interestingly enough, if either M1 or M2 were 0, the tension would be 0. That doesn't seem weird to me. If this block wasn't, oops, can't do that. That block wasn't there, there'd be no tension in the string. There'd be no inertia in the system for which the string would be attached to create tension. So tension would be 0. And if this box wasn't there, there'd be no tension in the string either. Nothing to cause the box on the table to move. So that makes pretty good sense. If we look more closely at this, though, as M1 becomes small, then we see that we'll get M2 over M2, and it'll approach G, but it'll never be G. If M2 becomes small, it's likely that the system won't accelerate at all. So that's looking here at the acceleration. All right, if M1 becomes small, then the denominator becomes just M2, and M2 over M2 just gives us 1 times G. So if M1 wasn't here, M2 would just fall at G. But if M2 were small, it's in the numerator. I get a small number divided by M1. That means it would approach 0. Would it ever be 0? No. Even if I hang just a feather off the side, if there's no friction, I'm likely to accelerate the box even a little bit. But it gets closer to staying still if M1 is much bigger than M2. Those kinds of questions you should expect on your test. The ability to do an analysis like that. That exact discussion about M1 being big compared to M2 or M2 being big compared to M1 has been on the AP1 exam in the FRQ section, asking for you to identify arguments that both support or deny claims of any way there's the acceleration of 0 or acceleration of G in a problem like this. All right, I think I've talked this one into the ground. Any follow-up? All right. So I think there's only one. Now, as I set this problem up, let me just tell you a few things. I believe this is probably enough of a review, but if you find that you need help, then stop in early on Tuesday morning and I'll be here for you. I don't want to do the whole thing because if we assume M2 is bigger than M1, and we've done this problem before, we get M2G minus M1G divided by M1 plus M2. We got to this point in class yesterday, so am I okay to stop right there and just talk about this from this moment? If I wanted to devise a lab that could help us measure G, I could use this information to do so. I see a relationship here between the acceleration of the blocks and the masses of the blocks. Do you see such a relationship? It seems to me that if I wanted to measure G, then I would need an apparatus that would allow me to measure the two masses and also measure the acceleration of the system. So we've measured acceleration before of an object that's moving, and we know how to measure mass because we now know how to use a triple beam balance. With those two things, if I give you a variety of masses, you should be able to tell me what G is by measuring the acceleration of an outward machine. What I would probably expect you to do, and we're going to do this, and I might as well just keep talking because you guys pack while I'm talking, which makes me feel very, very bad about you and myself. I'd probably recognize that we could probably linearize this set of data. We're measuring that would be a independent variable, dependent variable. And we have choices over M1, M2. That would be my independent data. I could probably come up with a way to linearize the data in order to determine G from a graph. Now, I'm not going to ask that on your test, but I see no reason why that couldn't be our next lab. It looks like a pretty straightforward one. My intention is to do that next week, Wednesday, the day after your test. Grade our test first and then start this. Because then we have Thursday for Veterans Day. This seems appropriate.